Okay. I was supposed to start with good morning, but seems like it's good afternoon already. My name is Nikolai Marekov, and I'm a QA with Experian for almost 6 years, working in the analytical team of Experian, developing analytical applications for the company. I'm a graduate of Applied Math from the University of Sofia, and I'll be joined by Dimitar from the development team for this presentation.
Hello, my name is Dimitar Atanasov. I'm a technical architect at Experian. I work as a software developer for 10 years, and from 6 years I'm working on the analytical solutions of the company. So today, me and Nikolai are going to present to you our experience developing high-performance analytical applications. And we would like to show you how important is the involvement of the QA team in doing such type of projects. But let's first, Nikolai, tell you a little more about the software.
So first of all, who we are. Experian is a global company present in 40 countries and operations in 65 countries. And the main business of Experian is to analyze huge amounts of data and provide risk management solutions and support for customer management of companies from the financial sector. And in doing this, we have a lot of software that helps us support this process. And one of the softwares that we're going to present to you is called Model Development Studio, or shortly MDS. So just some history. It's a Java application which has been developed for 5, 6, 7 years, maybe. It's usually used as a standalone tool by our analysts within Experian, so it's usually used on a laptop or a desktop. And an analyst would usually use the laptop within a client's premises, so it has to run on a laptop, basically. It's used for data investigation and statistical modeling, so you collect information about the data, and then you're modeling. A little bit about modeling you'll hear about it after that. Most people run away from the room when they hear about modeling, but it will be just explained in a simple manner. We use our own data storage. It's not any database or anything, because we come to the conclusion that it's easier and faster to implement our own data storage, because usually we read the data consequentially every time. Within the software, we have data for between 20,000 and 50 million people observations. Companies in the States would have information for up to 50 million people. And it will hold up to 2,000 columns or attributes of those people. So imagine how much information financial companies and companies from the financial sector hold about you. Like when you pay your credits, when you use your credit cards, when you buy a car, and all of these things are collected and analyzed within this software. Of course, not all of these attributes are statistically significant. So, for example, what color of your eyes usually doesn't have, it's not correlated to the amount of credit you have, or to the, whether you turn out to be a good or a bad customer. So sometimes data sizes range well over above 20 gigabytes, so it's important that we sometimes process this quickly and develop models quickly. So what's a model then, and what actually the studio produces? So that is a simple example of a model. Imagine that you go to the car insurance company and want to pay your car insurance. So a model actually tries to find some trend or some correlation between an input characteristic, in this case is the horsepower of a car, and the probability of you being involved in a car accident in the next year. Because if the probability is higher, then the car insurance amount will be higher. So, as I said, the model can be seen, a linear model, it can be seen as a trend between an input characteristic, horsepower, and the probability of an accident. And this trend is usually described by a formula. So the probability of an accident is some formula, and it depends on, in this case, on the horsepower of a car. So suppose you come in to the car insurance company, and you have a car with a horsepower of 150, quite popular horsepower, because you pay lower taxes in Bulgaria for a car with 150 horsepower. And this formula straight away evaluates what the probability of an accident would be It's about 20%. Well, models are not often that simple, and they would usually involve other characteristics or attributes in them. So imagine that you had no previous accidents in the last year, which would lead to in this case, to the probability of an accident decreasing to about 12% in this model. And imagine that you're younger than 23 years old, which will, in most cases, mean that you're not such a careful or not such a good driver, and this might, in this case, increase the probability of a car accident, in this case, to 24%. So what Model Development Studio does is actually tries to analyze big data and find some relationship between input characteristics like horsepower, number of previous accidents, or your age, and to relate them to an output characteristic like probability of an accident. In the financial sector, this can be applied very well indeed, because you can have like your salary, the things you own, and how often you paid your credits. This can be related to the probability of you being a good credit applicant. So this is how this software can be used in the financial sector as well. So now we have the business need of a product, and with the years, with the laptops having more processing power and better disks and things like this, comes the requirement. Our clients started requesting us to build better models. So better models usually means faster models, because they wanted their data analyzed faster. So there was a requirement to perform for our application to perform at least twice better on a standard laptop or a desktop. So how do you actually achieve this requirement, and how do you standardize the metrics, and how do you actually verify that you have achieved the performance will be the topic of the next presentation. But first, let's start with analysis of the requirement.
Okay, so now we have a requirement to increase the performance of the application. And such kind of projects usually have a lot of uncertainty in them, because this requires a lot of redesign of the system. Also, you are not sure everything you touch, how we will really increase the performance. So we should start with a well-defined strategy how to achieve that. And first, we should start with a well-defined goal. We have the right requirements. This is important not only to know what we are going to do, but also having an exact requirement helps us to measure at each stage of the project to know exactly how close we are to the final goal, to make some decisions which areas of improvement will be more valuable, where exactly our problems. So we can adjust better to reaching the final performance goal. So this, of course, includes a strategy how to develop that. We are going to touch the very core of the application, so we should be very careful and start with some proof of concept as a beginning. Also, this will affect all the reports we have in the system, so maybe we should start only with just a few of them to see how the things will actually work. So this cannot happen, of course, without the know-how of the development that has in-depth knowledge about the software, and also the developer should be capable of doing some research in the areas of improvement and so on. But development is not the only thing that we should do. We should, at each step, the QA team should be prepared to measure the exact state of the system. How fast are the reports now? How right is the results that they are producing, comparing to the state before the performance improvement project? So they should prepare some framework for evaluation and validation of the results. Of course, no matter how good we are prepared for all this, there is still a lot of uncertainty involved. So the project should proceed in small iterations, including developing something, then testing it, giving some feedback to the development team to know where to concentrate their efforts, and so on. Developing something, testing it, feedback. This way, we are very flexible and can achieve our goal with as much certainty as possible. So this is the strategy that we had in the beginning. And first, we have the requirements. Now we should analyze the system and see what can be done. So what the application is, we have all the data stored in a monolithic file, single monolithic file. Then we process it row by row and aggregate some statistics, some correlation matrices, or some other mathematical stuff that is then statistical stuff that we use later for the reports. So what's the problem? That we as Nikolai said just ago, that it was a legacy application. So it was developed a long time ago, and it still reads all the data every time and process everything in a single thread. So you can see on the graph here that run on an 8-core machine, it utilizes only one of the cores. So this is one area of improvement that can affect the performance very much. So analyzing the system came up with a few areas of improvement. First, of course, is to make it multi-threaded and make it scale over all available cores. Second, we can improve the data storage because the data should be read every time for every report. And at the end, if that's not enough, we can still think of some pre-calculating the data or some caching and so on. And before we can start developing this, the QA team can start developing their framework for evaluating and testing the application. So let's see.
Thank you, Mitko. So even if you have like the best solution of a problem or of requirement, it's still a matter of having the right means to measure it and having the right means to just see the progress of the development at each stage. So it is really important for the QAs to step in at the very early stage of development and develop like a testing strategy or a framework. So this is what the QA team did. First, selecting a number of different projects, like data set sizes. Luckily, this, as Mitko said, this was a legacy product, so we did have a lot of usage statistics about the product, so started analyzing those usage statistics and selecting some projects of different data sizes. So we've had like projects of a lot of observations and not so many attributes, or projects with a lot of attributes, like hundreds of them, and not so many records, and so we selected a bunch of different data set sizes on which to test the performance on. One other thing we did is we analyzed the usage statistics of the different tasks within the system. So, for example, some reports or some tasks were run more often than others. And in this case, for example, data investigation or collecting statistics was used much more often than, for example, logistic regression, which was a modeling tool or a modeling task. So what we did then, we set up a linear workflow. We used QTP. QTP was just had been used in the company for a while for automating this product, and we decided we didn't need to invent like the wheel or change the tool. We just wanted to set up the right workflow and the right measurements. So we did use the QTP linear workflow. So these were different tasks which were just the workflow represents different tasks, and each of the tasks were assigned a different weight, depending on how often it was used historically on a client system. So we also tested this on T2 for 8 and 16 cores to test for vertical scalability. This actually, even before development started, this actually meant that we can have reports from the whole workflow each and every day or each and every build that was produced. So as I said, QA, developing a QA strategy or a metric, even before the development starts, can sometimes really speed up the development process. So let's see how development progressed.
Okay, so now we have a way to measure what we're achieving, so we can start developing. First, we start with the multi-threading as most promising one. We implemented a classical producer-consumer pattern as producer reading the data store and reading chunks of data, put them in a working queue, where some consumers pick them and process them. The number of the consumers is exactly equal to the number of the cores in the system, so we are about to utilize the whole system this way and balance it with the working queue. But of course, when we use more threads reading some data, we should still aggregate in the same data object. We should aggregate the statistics in the same data object. So now we have more threads accessing the same data. And of course, this leads to a race condition. When we have two threads working in parallel on a shared data object, they read the value in parallel, increment it in parallel, and then set it back to the data object that causes errors when we have no synchronizations between them. So first thing we can do is to make the code synchronized. But let's see what's going to happen if we make the code synchronized. First will come the first thread that will obtain the lock and start executing the code. In this time, all other threads that came will just stop there and wait for the first thread to finish and release the lock. Later on, the next thread will obtain the lock, and only it will work in the code. So this way, we have, again, a synchronous execution of the code. Only one thread is working at the same time. So we actually did nothing. We're back to square one. So synchronization is not an option. The other option that can be used is atomics. Atomics are faster than the synchronization, but they also include some implicit walking behind them. So they are faster, but still not fast enough for our case. So what's the solution? The solution that we came up was to use a local data. Each thread uses its own data object, aggregates the statistics into it, and this way we have no interlocking, no synchronization, and each thread runs as fast as it can. And at the end, the only thing left is just to merge the results from each thread to merge them in a single final result. How we did this? We used some very useful API existing in Java. It's called thread local. It makes all the threads still use a single object, the thread local object, but in the background, when they are calling it, they receive its own copy of the data. So this way, they work with. It looks like that they work with one object, but in the background, each of them works with its own object. So we achieved what we designed, and we would like very much to see what's the results from the QA team.
Not enough. Looks like from the first testing that we did after development implemented this, it looked like some reports were significantly faster than others. Like some reports which didn't read in a lot of data were actually faster than twice. But unfortunately, some reports which collected information about the whole data file and read the whole data file, the improvement there was only 33%. So an overall of 1.67 times faster performance was achieved on the whole project data, on the entire project set. So then we sat down and started thinking, what would be the problem? Why would some reports which involved reading a lot of data not be so fast? So turned out the bottleneck, once we resolved one of the problems in collecting statistics and making calculation faster, is that we hit another bottleneck, and it was the disk usage. And you can see that from one of the just simplified example of how the input-output operations were significantly high. And this was actually turned out to be slowing down some reports, which required a lot of reading from the disk. So it was then time for development to step in once again.
Right. Okay, so thanks to the valuable feedback from the QA team, we know exactly where's our next bottleneck, and we can start working on it. So we now should optimize our data storage. Until now, we had the data stored in a single monolithic file. And if you want to read only the data that is required for a particular report, we need to read only just some of the columns in the data file. So we should separate them in separate files, so we can read only only the things that is actually needed. Maybe some of you will ask, why don't you just read the right information from the big file? And the problem is that if you look in the detail, how we in the low level will read the data file, we should first seek, let's say we want to read the power, only the power column for our report. We should first seek to the first element of the power column, read it, which is a very small amount of data, then seek again, read again a very small amount of data, and so on. This way we make a lot of seeks and reading just a little bit. So this is quite a slow operation in contrast to the case where when we have a single file, we just seek once and read as much data as we need. And it turns out that the second approach is a few times faster than the first one. So we expect this to increase our performance of some of the reports very much, having in mind that in most of the cases when the analysts that use our tool start with a lot of characteristics, but it turns out that only just a few of them are correlated to the output characteristic we are modeling. So most of the reports are actually run only on around 10% of the data. So this way, we expect to make these reports a lot faster. Let's see what the actual results were.
Yeah, remembering the example in the beginning, you probably remember that the probability of car accident only depends significantly on things like horsepower or number of previous accidents or the age of the driver, and there are a lot of other characteristics which are not used by some reports. So this expectedly has increased performance because most of the reports would now read only the data which was needed for them and then would read them in a faster way than before. Turned out the result was, first of all, just a quick check whether the input-output operations were, how it affected them, and it looks like we're now reading a lot less information than before, which is no longer a bottleneck. And second of all, we had a decrease in performance in one of the tasks. So instead of first increasing performance, reading in the data from an external source actually had degraded in performance because now, instead of storing the data, reading it in and storing it in a single file, we now stored it in as many files as we had characteristics. Luckily, we had a workflow, and the workflow had some weights on it. And importing of CSV data was only used once per project usually, while other reports were used hundreds of times per project. And while the reading in of the data decreased because of the change in the data storage, some reports, performance of some reports increased 12 to 13 times on different configurations. So at the end of it, we had an increasing performance of the whole workflow between 2.38 and 5.65 times, depending on the different configurations. So looks like, first of all, the performance target has been hit. And second of all, it does look that the improvement is, although we kind of expected it to be linear, to scale vertically, it wasn't quite the case. And might be any suggestions why we didn't achieve a linear improvement in performance? If not, I'll let Dimitar explain.
Developing such a performance optimizations project is usually working, fixing some bottleneck, then hitting the other bottleneck, fixing it again. So in our case, we still have, when we have too many cores, the performance is not, the calculations is not a problem anymore, but we hit, for example, the throughput of the disks, so we can just switch to faster disks. And also, we have some operations that cannot be parallel and multi-threaded, like inversion of matrices and some other things that there is no algorithms that make them parallel. So we hit the next bottlenecks in this case, and this is why we have only 5 times improvement on 16 cores.
Okay, let's accept this explanation. We're curious after all. We only care about numbers and how performance is improved. And as I mentioned, obviously this solved, we reached the target, this solved the problem. We are 2.38 times faster on a 2-core laptop, so we're fine with this. But then we started finding and discovering some calculation problems, and our automation framework allowed us to discover a few problems with the calculations, which we want to outline to you. First of all, there were some inaccuracies in the calculations. As like you can see in the 15th digit after the decimal point, there were some differences with the calculations before we started any changes, and after that. So this is the first column, is the before, and these 2 columns are the after results after. And more importantly, we didn't get consistent results, even with the same build running some models twice or many times. We would still have inconsistencies in the results in the 15th or 16th digit. And this looked like a problem because it would break all the test cases, and the Tamagotchi would be mad and would zombify and would eat us all. So we would want to just rectify this.
Any ideas what can cause such a problem?
Oopsie.
So it was really quite unexpected for us too. So it turns out that the cause is that the order of addition is changing the final result of the calculations. Quite unexpected, as you know from the mathematics, that this should not happen. But what the problem is? The problem is that in the computer systems, we should represent all the decimal numbers in a binary format. That means that even a simple number as 0.1 should be represented in powers of 2. So it should be represented in something like that. But unfortunately, it cannot be represented exactly. So always a small error that is in the final bits of information that is in the representation. So when we are processing a lot of data that has a very small and very significant numbers after the decimal point, this error actually affects the result, and we get slightly different results each time. So how can we solve that? We have 2 options to solve this problem. First is to increase the accuracy of our calculations, but this will affect the performance very much. And the other option is just to accept it and make it and use only the significance that we have. So it was very useful that we catch this, our QAs catch this early in the project, so we can now go to the business people, ask them, is this precision that we have now good enough for you? And the answer was that 12 digits after the decimal point are good enough for them, and the only thing left to do was to QA team to make all their tests for the output of the reports to make them rounded to the 12th sign, and
voila, all the tests would pass. So thanks, Dimitri, for pointing out how important it is that automation is not only important for measurement and for tracking the results, but also for early detection of problems, which can be then communicated to the users, and even before the software is actually released, these problems can be communicated and eventually solved. So having accepted this defeat from a QA point of view, and having modified the test cases to pass, we then stumbled across another problem. It was related to random sequences, and not a lot of people understand random sequences and why they're random and why they're not so random, and why they would have to get the same sequence every time you produce a sequence with the same ID. But let's try and just explain why they're important in the software in model development. Models are usually developed on a subset of the data called the training data, and the reason for this is that you don't want to overfit the model, or you don't want to come up with a formula which explains too well a relationship between the input and the output data, because it might not work so well on other data. So analysts would usually model train a model on a training sample and then validate it on a separate set of data. It is important that this training sample and the validation sample, although they're generated randomly, they're consistent with each report. So you don't want to develop a model on the training sample and then validate it on some other sample which is different from the validation one. So how an analyst would typically produce this sample is by a random characteristic. And a random characteristic with the same seed would actually always produce the same random sequence of numbers. So, for example, you get record 1, and there's just some random number returned for record 1, and since this satisfies the condition that random is bigger than 0.75, this record would go to the validation sample. And then if you get record 2, for example, and it gets a second number from the random sequence, it will go to the training sample. And it's important that each time random sequence is generated, it returns those same numbers, and these two populations are consistent. It turned out, after the changes of multi-threading were made, that this was not the case, and we would get different populations after on each run of each report, for example, on the validation sample. Any ideas why would this be the case, or should I just give the word to Dimitar? Sorry?
Multi-threading, because of the multi-threading operations that are being done, the calculation is going to be using different numbers.
Multi-threading is actually the greater part of the explanation, but it's not actually producing different results. It's what Dimitar might explain in detail.
What's the cause? So in a single-threaded environment, we process the records each time in the same sequence. So this way, each record receives exactly the same element of the random sequence each time. But let's see what is going to happen when we have a multi-threaded environment where there is no guarantees about the order of the processing. We can get record number 3 handled first by, let's say, thread 2, and if we call the random function, it will return to it the first element of the random sequence. Later on, the first record will get the second element, the second record will get the third element, and each time this will be different. So instead of random sequence, we get just random. Everything is random. So how can we solve that? Of course, we can assign some IDs that mark the position of the record in the sequence, and try to calculate directly the corresponding number from the random sequence. But unfortunately, there is no such algorithms that provide that. So in order to, when we have record 3 coming, handled by thread 2, we should calculate its corresponding third element of the sequence, but we have to calculate the first two before it. And in order to not to do that every time, to calculate everything before, we just put them in a cache, a simple solution that allows us, when later on comes record 1, handled by no matter which thread, we just pick from the cache exactly the element that is requiring and return it to it. And so on with the record 2, it will get its element of the sequence. So this is how we solve that. And let's see, is there any more problems in the tests?
Well, there were some. This is the always popular out-of-memory exception that we used to hit a number of times when running the automation workflows. At some point of the workflow, you can see there are seconds from the execution of the workflow. All the memory would be used, and well, for QA, it's very easy to discover such an exception, but probably for a developer, it's not so easy fixing it. So let's see how development fixed it actually.
Well, really, out-of-memory exception is the worst thing any developer can get, because the problem is always not where you expect it to be. It's somewhere hidden. That causes the problem. But in this case, we pretty much knew what can be the cause. And it is that when we have a separate data object for each thread, we actually get a number of times the memory consumption of the application before that. So when we have a 16-core machine and we run the application on it, we will have our data multiplied 16 times. And when before that the application was not meant to run in such an environment, there was a lot of excessive data in the data objects. So it causes the out-of-memory error. So during the whole development of the application, you should, when we are doing such an approach, you should always have in mind to keep the data in the data object as small as possible. So solving this allows us to finally scale over all available cores of the machine. We get a great scalability. You can see we utilized all the cores available. It even makes us think about further improvements where we have even more cores, like in the GPUs. And of course, in order to do that, we should again make sure that we have a very well-developed framework for evaluation of the system that is developed by the QA team. So
it's time for something of a conclusion then, something of an overview. Well, OpenCL modeling, random sequences, what was that? That's data storage, all these things you might not even remember after this presentation, but I think if there's one thing that you can take away from this is that you should have a very well-defined process when developing such a complex application. And even if you have a good, well-defined goal and a target, you need to have a QA strategy and QA framework before that, so that even before development starts developing, you can measure the result. And when they do some improvements, you can still say it's not enough, we didn't meet the goal. You can just get feedback right away. And when they make some more improvements, or you can just discover some issues with this, and when they make some more improvements, like data storage in this example, this testing framework can easily identify whether you met the goal or not, and can also measure adequately the results, and can help you discover any other problems which appeared along the development process. So as we mentioned already, integration between development QA from the early stages of development is the only way of developing such a complex application, and this is what we expect you to take away from this. Now we're even drinking from the same glass of water, because we're kind of from the same team. Okay, thank you. And any questions? Oh, wait.
So, MDS is a very complex product, but my question is, how did you manage to create the right test? To be sure from the beginning that you're measuring the right thing. Even more, there are different aspects, different bottlenecks. How did you manage to create the right tests?
Well, actually, I don't think we can ever just have the perfect test and perfect framework of measuring something. But as I said, analysis of the historical usage of the software and analysis of the fact that MDS actually had a task log and all of the task logs were created. Like, for example, we collected all the projects which were developed within Experian for a year or two back, and we analyzed all the task logs and saw what tasks were used and how they were used. So actually knowing your application and knowing how users would typically use it helps a lot. I'm not saying that anyone can develop a perfect testing framework or select the perfect test cases even. But knowing your clients is a good way to start.
Thanks.
Mm-hmm. Clock says 0. Maybe it's also time for lunch, so if there's one more question, or if not, then thank you. Okay.